Hi, everyone. Welcome back. We have another talk for you, another exciting security talk for you. Securing Kubernetes with Trusted Platform Module, presented by Alex Tcherniakhovski and oh my God, Andrew Lytvynov, Google Kubernetes engine engineers on the security team. Please make sure to rate the talk online after the talk on the Shed website. And if you have any questions after the talk, I'll be running around with the microphone.
Cool. Thanks, Maya. All right, so this is Securing Kubernetes with a Trusted Platform Module. Maya already introduced us, so I'm Andrew, this is Alex. And we're going to talk to you today about Trusted Platform Modules, or TPMs. Who knows what a TPM is? Awesome. Who used one, actually, like programmed something for it? Sweet. OK, for those of you who actually haven't used it a lot, TPMs are small crypto coprocessors. They can be a hardware chip like in this picture. They can be a software implementation, for example, in your hypervisor or your firmware. They are meant to be cheap and relatively low-powered, so they don't have high throughput. They don't have a lot of memory, but they still have a lot of useful functionality. The spec for this is designed by the Trusted Computing Group, which is an independent industry organization. And they have two mainstream versions of the spec, but we will focus on 2.0 for this talk. Just to set some expectations, for this talk, we are not presenting an existing project that you can just leave and like flip a switch in your cluster and use. This is more to match some of the capabilities of TPMs to the Kubernetes world and sort of fuel further work by SIGAuth or any of the other people interested in this. OK, so we will try to tackle some pretty tricky security problems that we face as GKE for hosting Kubernetes, but anyone running a cluster will also sometimes have to think about. The first one of these is no trust bootstrap. And this is essentially how do we provision credentials for a kubelet in a trusted way from the very beginning, and also how do we trust those credentials going forward. And also make that automated without any human involvement. Second problem is the first secret problem. So any sensitive data in etcds, such as secrets, we want to encrypt in transit at untrust. When you encrypt them at trust, you essentially encrypt a bunch of data with a key. Well, how do you secure that key when it's supposed to be available in master and protected from a compromise? The first two problems we have made proofs of concept for. We don't have the time, unfortunately, to talk for all the demos, but trust us, they work. The third one is a little more theoretical. We haven't actually we didn't actually write any code to do this, but in theory, it's supposed to work, and this is the tamper-evident audit logging. Audit logging on its own is a straightforward problem. You just log everything that's happening to your resources and ship it over somewhere. But to make them tamper-evident, you have to think about what if attacker actually compromises the thing that writes those logs and modifies them, deletes them, and whatnot. And we believe there's a solution to detect any tampering after the fact. So for this talk, we'll start by briefly covering some theory, some features of the TPMs that we'll use, and then we'll tackle those three problems one by one. OK, so some theory on TPMs. Some of the use cases for TPMs out in the wilds currently in use that's outside of the Kubernetes world are platform integrity. So for example, you have a corp laptop. How do you verify that it hasn't been compromised, tampered with, and before letting it onto your corp network, before shipping it any software updates and things like that? The other one is full disk encryption. So BitLocker and dmcrypt, for example, will use TPMs, if they're available, to protect the encryption keys used for actual encryption. OK, the main selling point of TPMs at a high level is memory isolation. TPMs live in a separate world of their own outside of your OS, firmware, or bootloader. And the software on your system interacts with them through a set of very specialized commands. It's a simple request-response protocol. And the TPM is completely passive. So unless the system asks it to do something, it doesn't do anything. TPM has two types of memory. So the runtime memory, same as your RAM that's swiped on reboot, and non-volatile memory, which is persisted across reboots. There are commands that allow you to read and write this non-volatile memory arbitrarily, pretty much, as if it's just another little disk, but you cannot read the runtime memory directly. You can only interact with it through very specific commands, and none of the data in there is available to fetch out of the TPM. And the main threat model they are meant to be used against is when your OS is compromised, when you don't trust all the software running that's outside of the TPM. You want to protect some very, very sensitive small pieces of data or credentials. Let's cover a few features we will use. First one is TPM keys. These are cryptographic keys that are stored in the runtime memory. Those are your typical RSA or elliptic keys, symmetric, asymmetric, whatnot. There's a lot of attributes. You don't read them directly because they reside in the runtime memory. You interact with them through specific commands, such as sign this blob or decrypt, encrypt, things like that. But you don't actually have the key in your memory yourself. Next thing is endorsement key. So this is a special type of key that's baked into the TPM. And to match that, a TPM vendor will also sign a TLS certificate and put that into the non-volatile memory. This key and certificate are supposed to act as machine identity. So if you can prove that you have both of those, you prove that you own the TPM, and no one else is theoretically supposed to be able to do that. Next, we will cover PCRs and measurements. Measurement is just a fancy crypto word for hashing something. So if you want to measure, for example, your kernel, you just run it through a hash function, and the resulting hash is called a measurement. This is used, for example, in something called measure boot. So when your machine boots, it goes through a sequence of steps. So it starts with bootloader, then goes into firmware, then goes into your kernel. Those pieces of software pass execution from one to the other. With measure boot, before passing execution to the next step, they will actually measure it. So they'll hash the binary of the next step, record that in the TPM, and then pass the execution onwards. What it does is if an attacker modifies any of the subsequent pieces of software, that will reflect in the measurement, and you can detect it and do appropriate action. These measurements are stored in the platform configuration registers, or PCRs. These are like tiny little registers in the runtime memory of the TPM. They are bound in number. They have defined purposes in the spec. For example, PCR 7 will be used for secure boot information. And the value you put in the PCRs is not written in directly. You don't just set this PCR to this measurement. You use an operation called extend, which essentially concatenates the existing value with the new measurement, hashes that, and gives you the new value of the PCR. That means that you can record a sequence of measurements in the same PCR without blowing up your memory. And as long as the sequence is the same, the PCR value will always be the same. So you can record multiple steps of your boot process, for example, in a single PCR register. There is a ton more functionality that TPMs provide, but we don't have the time to go into that, and we're not going to use them for this talk. But there's going to be a link to the spec at the end of this, at the end of the slides, and feel free to read and come up with more creative ways to use it in Kubernetes. But this is a very complicated and functional piece of technology. Okay, let's finally jump into the fun parts. Let's tackle our security problems. The node trust bootstrap is first. As I described before, is just how do we provision credentials for your kubelet in a trusted way. Kubernetes, for that, provides a very handy API called the Certificate Signing Request API. So your master serves that as it's a Kubernetes-style API served by master at a very, very high level. It works this way. Kubelet sends a CSR request. Master does some validation. Kubelet approves it, sends back a certificate. Before we jump into the details, the threat model, we will try to implement this under is an attacker that can compromise a pod. They can break out of the pod, they can compromise the node. So we assume they have full root access to the node. Usually they will try to go after application configs to sort of get some reconnaissance data on your environment, move laterally. They will try to maybe steal your secrets to access some sensitive data, and usually they'll want to persist this access for as long as possible to catch any future data that comes into your cluster. All right, so in the CSR API, what we want to prevent is two things. First, we want to prevent the attacker from abusing this API to mint new credentials pretending to be a node. We also want to, as much as possible, limit the attacker from stealing the credentials that the node has already provisioned and using it offline. So the certificate send request API is named after the X509 protocol CSRs, and that's the standard protocol that certificate authorities use to request and issue certificates. The way CSRs work in that protocol is you have your CA, you have your host that wants the certificate, the host creates a public-private key pair locally, then they start creating the CSR, which is essentially just the public key, some metadata such as DNS name, IP address, use cases for this certificate, and then a signature of those two things with a private key. The host then sends that over to the CA. CA does some validation, uses private key to sign it, and sends back the certificate. The important point here is that the private key never leaves the machine that requests the certificate and is meant to be always kept secure, while the public key can travel freely. In the CSR API in the Kubernetes world, your node is your host, your master controls your CA. So node creates the CSR with the key pair, and sends it over to master. Master does some validation, signs that with its local CA, and sends back the certificate. So we essentially scope down the problem of this trust bootstrap down to validating a CSR request from an arbitrary machine somewhere on your network. The naive approach to fix that would be, for example, let's issue a shared credential to all the nodes, same credential everywhere, and master also has knowledge of this credential. This will be done by your management plane, so your cloud provider or whatever else that spins up your VMs and configures them. That credential is stored on the node. It's passed along as a bearer token with the CSR request. Master checks that and signs the certificate and sends back the certificate. This is a pretty weak implementation because if our attacker can compromise a node, they can just wait for that credential to appear, grab it, and mint arbitrary node identities. It can say, I'm node A, I'm node B, and master will just trust it. We can do a little better by issuing credentials that are unique to that node, so each node gets its own unique credential. But it's still not great because the attacker can just wait for the CSR process to complete. They can grab that node credential off of the disk and just pretend to be that node. Just slightly better. You can't mint arbitrary identities, but it's still pretty bad. It doesn't accomplish our goals. So let's finally get to use our new fancy TPM for this. As I mentioned before, TPMs come baked with the endorsement key baked in, which is meant to act as an identity of that machine. So our idea is we will use that key to sign part of the CSR to prove that we have the endorsement key itself, and it will also attach the endorsement key certificate along with the request. So Qubit, as before, creates a public-private key on disk, signs the CSR with the endorsement key, sends over the CSR blob, endorsement key signature, and the endorsement key certificate. Master, which knows about the certificate authority that TPM used to sign this EK certificate, will validate it. It will validate the signature of the CSR blob. And importantly, it will also check the intended membership. So is this node expected to be in this cluster at all? Because otherwise, any node that has a TPM for exactly the same vendor could just pretend to be a node and get a certificate. So then it issues the certificate, sends it back, and it's stored on disk. OK. So that doesn't really solve our second problem, attacker just waiting for that whole dance to be finished and just grabbing the certificate after. So why don't we just put in the TPM? Because that way they can't exfiltrate it. So the idea here is exactly the same as the previous example. The only difference is that we start by creating the key in the TPM instead of on disk. And then we just go through exactly the same step. We sign the send the CSR with the AK, send that over to the master validates it, validates membership, and sends back a certificate that's stored on disk. So it's okay to store the certificate itself on disk. Without the private key, you can't really use the certificate on its own for a TLS handshake. And the attacker can no longer steal this private key to do node impersonation offline. So they need to be physically in a node. They physically have to execute code on the node every time they want to do a TLS handshake to talk to the master. So it's not like a perfect solution, but it's about as good as we can do given that our attacker has root access to the node, right? The good things here, we can immediately lock down this like if we figure out a way that attacker used to get into the node, we can immediately lock them out, and that locks them out from using those credentials when they can no longer execute code on the node. Also, we're using an industry standard for this. So this solution is relatively portable and can be used on-prem on different cloud providers. So this was Node Trust Bootstrap, and I'm going to hand it over to Alex to talk about the other two problems.
So in this section, our talk will examine probably the most common use case for using TPM, which is storing credentials at rest. And by credentials, I mean things like API keys, passwords, service account tokens. So to make this discussion more concrete, we'll examine how TPM could be used while integrating with key management services. So concretely, Kubernetes, starting with version 1.10, supports integration with various KMS providers via KMS plugin. So how does this work? When Kube API server, for example, receives a request to create a secret, this secret is passed over a Unix domain socket to KMS plugin. KMS plugin, in turn, orchestrates interaction with, for example, Google Cloud KMS or AWS Cloud HSM to encrypt the data. Eventually, Kube API server receives the encrypted payload and passes it over to etcd already in the encrypted form, where it is stored in etcd, stored on disk in the encrypted form. I purposely omitted a lot of details from this flow. We have a link in the reference slide to a prior KubeCon talk that discusses KMS plugin and envelope encryption in more detail. So if you're interested, please take a look. So in our threat model, we assume that, attackers have complete access to an offline image of the master. So think of a scenario where attackers were able to get a backup of the master VM, or they were able to get a clone of the master VM. We also need to assume, because we're interacting with cloud service, that KMS is accessible over the internet, and that KMS plugin must be running in a security context that allows it to make encrypt-decrypt calls against the KMS. So this introduces what we call a first secret or last mile problem, where the fact that KMS plugin must have the security context to interact with KMS, it must have a credential in order to bootstrap that trust and issue and request an OAuth token for the KMS service. However, this is the important part. If such bootstrap credential is persisted to disk alongside the etcd data file, then we haven't really achieved anything, because when attackers get that offline image, they can extract that credential and start making calls to KMS and unwrap our secrets. So therefore, our core design objective here is that at no point in time we should be storing credential for KMS on disk, which we assume attackers will have access to. So I'm pretty sure you already know where this is all going. Yes, we can use TPM to seal KMS credential, and instruct KMS plugin to unseal this credential at startup time. So what does it mean to seal, unseal? So Andrew mentioned TPM supports has this concept of keys, which are managed internally. So we can use one of those keys to encrypt the, let's say, a service account token, which is stored on disk. So that basically solves our threat model where the credential is now stored on disk, but it is encrypted by TPM. And KMS plugin at startup will interact with TPM, unseal the credential, and place it in its memory. So therefore, at no point in time are we storing the credential on disk. We can extend this model a little bit further into the online attack world, where we can leverage PCRs. So Andrew talked about measure boot, where the basic idea being that you can make assertions about the state of the system by looking at the PCR registers. And if the PCR register is indicative of the state that you trust and verify, you can take those registers and you can create a policy out of them, which can be assigned to a key. In other words, we can log the use of this key to the specific state of the system. In other words, if attackers were able to inject a rootkit or something along those lines, then the key will become unusable because the state of PCRs will differ from what the policy states. So where do you go from here, assuming you're interested in this approach? How would you implement it in your environment? So you have two options available to you. You can use a Go TPM library, which thank you, Andrew, for being a great contributor there. I have an example here, TPM seal unseal. It's about 40 lines of Go code where you can instrument your application to seal and unseal secrets from TPM. This is available today. If you prefer to keep that logic out of your core application, take a look at another project called TPM2 Tools, where you will find command line utilities which allow you to interact with TPM. So you can think of like, for example, an init container, which will start up, unseal the credentials, and place them on a shared volume for your main application to use. OK, I think that's all I have to say about first secret problem, and let's move to the tamper-evident audit logs. So if you're not familiar with the idea of tamper-evident logs, it will become fairly clear when I describe the threat model, so just bear with me for a minute. So we're back in the same scenario of using KMS plugin with the goal of protecting our secrets, encrypting our secrets. But this scenario is very different. In this scenario, we're assuming that attacker has root access on the live master host. And the goal of the attackers is to exfiltrate the secrets from the master and use them somewhere else. In other words, for attackers, this is just a stepping stone. They're not actually particularly interested in this particular cluster. They're after some other system, and they want to extract the credentials undetected without raising any alerts and use those credentials somewhere else. What is our goal? Excuse me. Of course, we want to detect that compromise, and we want to revoke the credentials. The part of being not discovered is very important here, which implies that attackers will try to cover their tracks and will modify the audit log entries. Let me first explain how TPM auditing works. TPM auditing works very similar conceptually to measure boot. In measure boot, we're measuring the software, the sequence of different pieces of software that execute during boot. With audit logging, we measure the sequence of commands that TPM executes. So what is the measurement of a command? Let's take a command. For example, TPM has a command, TPM2HMAC, which generates HMAC. So that command has a unique code in TPM. And we take that unique code, the inputs to the HMAC function, its outputs, concatenate it all together, hash it, and then extend it over the audit register. And audit registers are similar to PCRs, but they are, in fact, similar pieces of hardware on the TPM. So let me take a look at it. Before I jump into an example and explain how that works in practice, I wanted to explain probably an obvious thing, that TPM is a very memory-constrained device. So we can't just write log entries into the TPM directly. It's just not possible. It just doesn't have enough memory. This means that we should be able to safely store our log outside the TPM on disk, because audit log may grow quite large. However, as you will see, we can still detect tampering by virtue of the TPM. So let me set up this example. In this example, I will assume that Kubernetes CA, certificate authority, uses TPM sign operations in order to sign certificates. By the way, this is another great use case we didn't have time to cover here. But imagine taking the signing key of the Kubernetes CA and placing it in hardware. That dramatically improves the security posture of your cluster. So, but back to my example, we issued the first certificate, and in the log maintained by the CA or by proxy, that proxy is the request to the CA, we wrote exactly the data. In fact, that is a CSR that was signed by the CA. Also notice that the fact of signing that certificate request was issued a TPM sign to command, which we audit. And what we have in the TPM audit register is the digest of that operation. And you can imagine that goes on for a long time. Then we issue another certificate, and over time, the audit register basically reflects the life cycle, the whole life cycle of the CA. Then comes an attacker, and they issue a certificate number 3. And again, the audit register reflects that fact. So from attacker's point of view, dealing with the audit log is very simple. It's just a text file. They can go safely. They can easily remove that record from the log. However, the fact that they remove the fact that the certificate 3 was issued does not change anything with respect to the audit register. Attackers cannot roll back the value of the audit register back. It's just not something that TPM will allow you to do. So that's you probably already understand where this is going. We will use the fact that now the audit register does not correspond with the actual entries in the log. How do you catch attackers? It's a 3-step process. First, we issue TPM get command audit digest. This gives us the signed structure. It is signed by the key in the TPM, which contains the current value of the audit register. This also resets the registers to zeros. And then we're looking at our logs, and we start replaying the TPM sign operations. And once we're done replaying, we expect the value of the audit register to be exactly the same what we got in the step prior to the replay. And if the register do not match, like in this case, we obviously need to assume a compromise, because we need to assume a compromise, or at least we need to assume the tampering was logging. Because the state of the audit log does not correspond to the state of the audit register. There is one thing that attackers can also try. Attackers can also think in terms of what attackers can reset the audit register. They can set it to all zeros. It is something they can do. And they could be smart, and they can replay the legitimate certificates, and therefore place the state of the audit register in the state that we expect. However, TPM is smart in this respect. It will record the fact that an extra reset operation was performed. So therefore, on our validation step, we can detect that somebody reset the register without our knowledge. So are we done? I just explained to you how we can do tamper-evidence and how we can detect tampering with our logs. But I didn't really solve our original problem. Remember, our original problem was how we catch our attackers, in the act of extracting our secrets. Right now, KMS plugin and interacts with KMS without using TPM at all. So our objective is to place a call to KMS, to place TPM on path to call to KMS. And in the next couple of slides, I will explain how we can accomplish this by merging some capabilities of TPM and KMS. So I already explained how auditing works. We will need some additional capabilities from TPM. We'll take a look at how HMAC could be generated on TPM. And we will need something from KMS. So KMS must support authenticated encryption with additional data. And don't worry if some of these terms are new to you. I will explain exactly what we need to know in the next couple of slides. So first, let me explain what HMAC is, just to make sure that we are all on the same page, even though I'm pretty sure most of you know what this is. HMAC is based on hashing with the key exception that we use a key as an input to the digest. With the basic idea is that only that parties that possess the key can perform the authenticated measurement of the piece of data and can validate it. So TPM is a great device for generating HMACs. Why? Well, it manages its own keys. And number two, the operation, the cryptographic operation of performing the HMAC is actually conducted inside the TPM, outside the host main memory. So that's all we need to know about HMAC. Let's move to the authenticated encryption. So this is how you probably think about encryption. You supply the plain text, and you get the ciphertext back. So authenticated encryption with additional data throws a little bit of a twist into this. In addition to the plain text, you can supply AAD, additional authenticated data. Typically, AAD contains some metadata about the plain text. So if we use Kubernetes secrets as an example, a good piece of metadata about the secret would be the key that uniquely identifies your secret within the cluster, something like namespace and the name of the secret. So the important part about authenticated encryption is that when you perform decryption, you must supply the same AAD, additional authenticated data, that you use during the encryption operation. Otherwise, KMS will refuse to perform this operation. So in other words, we must ensure that AAD supply is the same on encrypt and on decrypt. And that is the key part that we'll use in our scenario. So now we have all the technology, we understand all the technology we need to build the solution, so this is the main idea. What if we use TPM to produce the additional authenticated data? Concretely, we can take the key of the secret, take it through the HMAC function on the TPM, which produces a value that uniquely identifies the secret. But the trick is that this value can only be produced on the same TPM. That can only be decrypted. This operation can only be reverse decrypted on the same TPM that produced the encryption. What this means, if we audit the HMAC command, when attackers want to exfiltrate the data, they will be forced to go through the TPM because there is no other way in which they can generate the AAD. And that will force the extension of the audit register, and we can basically use the same trick we used in the certificate example, where we can catch the extra decryption of the secret. So there is a couple of scenarios. There is a couple of vectors that this does not cover. Attackers can, by virtue of having root on the master, they can directly attack memory and extract secrets from memory. But the good news is that encrypted memory is apparently coming. There was a talk on Tuesday that talked about bringing encrypted memories into Kubernetes world. So by combining these two scenarios, you can actually even counteract this attack as well. Attackers can wait for the user to request the secret they're interested in. And that's a hard attack to deal with. But I would say that making attackers wait sometimes is a victory in its own, because the longer they have to persist there, stay on the master, the more chances we have in catching them. I want to wrap up with a couple of scenarios where we would not recommend to use TPM, because we describe a couple of scenarios where we suggest we use them. So TPMs are not really used to performance. Don't put TPM on a execution path, crypto execution path, where you have performance constraints. It just simply have not been designed for that. If you're using virtual TPM, that may not be the case, but check the latencies before you use it there. It is not used for bulk encryption. It's typically used to encrypt small pieces of data like keys. So think about not using it in those scenarios as well. Don't think of TPM as tamper-proof. It's tamper-resistant. There have been attacks against TPM where, through some chemical peeling, keys were extracted from TPM. So physical security still is a thing that you need to worry about. That's all we have. I think we have 1 minute for questions. I'm sorry, we went a little bit over.
So I wanted to ask, with the trying to combine KMS and TPM, how would we do that? Like if you have like multiple masters in HA, all of which have distinct TPMs?
Sure. Unfortunately, we actually had a slide to cover this scenario, but just couldn't fit it in. The basic idea is that the TPMs have the ability, you can create an exportable key in the TPM. And you can basically, when the master knows its neighbors, so to speak, basically you elect a leader. And that leader will generate a key. And it will encrypt that key to its neighbors, because it knows the public key of its neighbors, and it can safely pass that key to its neighbors, and they basically will use the same very key. So there is an extra step that you need to do, but it is something that it's a common enough scenario for users of TPM.
We actually don't have time for any more questions. So thank you so much, Andrew and Alex. Please rate your session online on Shed and come back for more security later.
We're going to be here. I know
Yeah.
we ran out of time, so if you have any questions, please come here, and we'll be happy to talk.